we looked at the normal distribution, and then we talked about the standard normal distribution. So it makes life easier if we turn every normal distribution into a standard normal distribution, because then that allows comparison. So I'm going to let Z be the standard normal distribution. So it has an average of 1 and a variance of 0. And you may recall that the formula for the normal distribution is 1 on root 2 pi e to the minus z squared on 2. That's for the standard normal distribution. Let's play with the graph. You have to remember this from when we did that curve sketching last year, what we do to it. Remember, function z divided by some constant. And that constant I'm just calling sigma. So you may recall if we divide it would have been the x value, in this case the z value, then it's going to be a horizontal stretch by a factor of sigma. So my function now becomes 1 on root 2 pi e to the minus z squared on 2 sigma squared. But if I stretch that curve out, I'm going to change the area under the curve. Okay? So imagine it was a rectangle. So at the moment it started with an area under the curve of 1, because we know all the probabilities add together to give 1. So the base times height of this rectangle would be 1. But if I was to stretch it out by a factor of sigma, the base is now sigma times b. So its area has just become sigma. We want to get that area back to 1. So how do I do that? I now play around with the vertical dimensions. So if I now stretch it vertically by a factor of 1 divided by sigma, then my area of the rectangle becomes sigma b times h on sigma equals 1. The sigmas cancel and I'm back to my original dimensions. So I've got it back to an area of 1. How do we do that algebraically? Well, now I divide the y value by the factor. But this time the factor is 1 divided by sigma. So we've stretched it vertically by 1 on sigma. So my function is now 1 on sigma, phi, God, how could I forget that one? It's one of my favourite irrational numbers, phi. Phi z on sigma is equal to that expression on the right hand side rather than me saying it all. Now, I'm going to shift the whole thing right, mu units. Now, shifting right, it was when we grouped it with the x value. Well, in this case, it's the z value. So I'm going to shift it and we get z minus mu. So my function now becomes this. I won't say it all, because I'm sure I'll muck up some of those letters in there. So what have we done? So what I've basically shown is that these two are in fact equivalent. I just stretched it and moved the curve, but now they're equivalent. That means any normal distribution with an average of mu, variance of sigma squared, I can transform into a new standard normal one, and the transformation is via this formula here, x equals z minus mu over sigma. That is a z-score. Standardization equation. There it is. And so when I give you your test back and you see your z-score on, that's exactly all I've done, is I've plugged it into that formula. Your result minus the average divided by the deviation. It standardizes the result, and then you can see, you can compare different tests, and you see, how many deviations was I above or below? When we talk about z-scores, we usually do them to 2 decimal places. So quartiles and outliers. So Q3, we know, is 75% of the data. So if I was to look up my tables, whatever the third quartile is, I know I'd come back with an answer of 0.75. Turns out, Q3 turns out to be 0.67. So yeah, if you were to put it into your calculator, for those that can, or look up on your table, you'll find that 0.6745 would return an answer of 0.75. Symmetry then says that Q1 is negative 0.675. So from there, I can work out the interquartile range. Difference between Q3 and Q1. And so it would be 1.35. Now, an outlier. You remember your definition for an outlier was 1.5 times the interquartile range above Q3 or below Q1. So in our standard normal distribution, anything with a z-score more than, well, to 2 decimal places, 2.70 would be considered an outlier. So we could say the absolute value of the z-score, because on the other end, then it would be less than negative 2.70. So the absolute value of the z-score, that would be considered an outlier. Now, if we were talking about your test results, being an outlier positive 2.70, that's good. Outlier negative 2.70, ooh, I'm not showing that to anyone. Time spent waiting for a prescription to be prepared. Normally distributed, average of 15 minutes, deviation 2.8 minutes. Find the probability that the waiting time is more than 20 minutes. So we have to wait for more than 20 minutes. So I'm going to let W represent waiting time. So we're saying the waiting time is normally distributed around an average of 15 and they gave me deviation, so variance of 7.84. So I want to find the probability that W is greater than 20. But look, they don't produce tables for every possible normal distribution. So we standardize it. We bring it back to the standard one using our standardization equation. So 20 minus the average divided by the deviation, it's 25 on 4, but I'm going to go 1 minus that because we want greater than, whereas our tables give me less than. And if I look that one up, there we go. So it's actually a very small probability that you would have to wait for more than 20 minutes. 0.0, well, almost 4% of a chance. The TQ company makes a soft drink. And we sell these drinks in 330 milliliter cans. Now, the actual volume of the drink is distributed normally. Some will have more than 330, some will have less than 330. The deviation, 2.5 milliliters. We want to make sure that every drink that we produce, well, it's going to be impossible to get them all right, but we want at least 99% will contain more than 330 ml. People aren't going to complain if they get more. They're only going to complain if they get less. So we want to try and get more than 99%. So V is the volume of the drink. And we're saying it's normally distributed. We don't know the average yet. That's what we're trying to work out. And our variance is 6.25. So the probability of the volume being greater than 330. So again, we'll use our standardization equation. Turns out that that one would be 0.01. So we just have to solve this equation. The number that gives us 0.01 is minus 2.33. Solving that, we get 335.825. So if we set up our machine, and instead of saying, hey, try and put 330 mils into every can, try and put 336 milliliters into each can, we should be okay. So we're going to try and put 336. A biologist, and they're looking at a cactus, as biologists, I guess, do. And they've observed that 34.2% of the cacti, and what else we got? 18.4% are above. So again, assuming a normal distribution, let's find the average and the deviation of our distribution. So H is the height of the cactus. So we know it's going to have a normal distribution, but we want to work out this time what the average and the, deviation is what we're looking for. We've been told that the probability of Z being less than 12 minus mu on sigma is 3.42, and probability of it being greater than 16 minus mu over sigma is 0.184. So we can now create some simultaneous equations. There's our two. The phi of 12 minus mu on sigma will be 0.342, whereas 16 minus mu would be 1 minus 0.184, which is 0.816. So there's my first equation. 12 minus mu is minus 0.41 sigma. And there's my second one. Two equations, two pronumerals. Should be possible to solve these simultaneously. And of course this is an easy one because the mu's will cancel giving me that sigma is 3.05 and the average is 13.25. Okay, 16E, 16F.